Hi everyone, welcome back. Can everyone hear me? Okay, thank you. Okay, so today we're going to start to talk about light and matter interaction. And okay, light matter interaction. And in previous week we kind of reviewed the Maxwell equation. Okay, the four equations. I won't repeat here. And then also we talked about how to use Maxwell equation. Okay, especially the these two, to get the wave equation of light, and then we derive the wave equation of light, and then get the speed of light. Okay, so this week we're going to start to go into the classical picture of light and matter interaction, and then we'll actually start with the simplest one. Okay, with the what we call linear version. Okay, so a fundamental question that we can ask ourselves. Okay, is that suppose we have light coming in, going through a media, right? Going through a media, and what can we expect? What will happen? Okay, in this case, there are a few that you guys are already, quite familiar with. First is that the speed of the light will change, right? There will be a refraction index that changes the speed of your light. Okay, and then the second one, there will be absorption. Most materials, even if it's transparent, it still have a little bit of absorption. The best case is actually when you, like water, right? Most of the time it seems transparent. But if you do a scuba diving, okay, you go a little bit deeper into the ocean, and then you look up, okay, it's actually quite dark. Of course, part of that reason is actually total internal reflection, but then a lot of, the reason is also water has absorption. And the third one is dispersion. Dispersion means that the velocity of the speed of the light actually has a dependent on wavelength. Okay, for example, well, you guys are all know this. For example, the Newton's prism or the rainbow, right? If you have a white light shining here, and then different color will go to different places. Okay, and then you can separate different color. Okay, for example, this is lambda 1, this is lambda 2. Right, dispersion. So what it really is the refraction index, okay, is a function of wavelength. So these three are the most common phenomena you will see when you shine a light into a material, okay, into any material. You probably, every time before you do an optical experiment, okay, before you do it, you actually has to check some tables and then know, okay, what's the refraction index? Does it have huge absorption? And then what is the dispersion relationship? Okay, and and this kind of, is mostly what we call linear, right? Because you see that the speed of light change doesn't affect doesn't affect the linear input and output relationship. So it's for the absorption, right? You double the input, you double the absorption, you double the output, right? So everything is linear in this situation. But this kind of three cases, okay, three features, can give us a very brief idea of how to think of light and matter interaction. Okay, so the classical model we're going to build, okay, to kind of give you an expression, although it's not accurate, but give you an expression of all these three features. They are all connected. If you take a closer look, they're all connected to the refraction index of the media, right? While speed of light, definition is here, dispersion literally means that the refraction index depends on wavelength. And then for the absorption, later you will also see that the imaginary part of the absorption, okay, the imaginary part of the absorption actually correspond to, well, sorry, the imaginary part of the refraction index actually correspond to absorption. Okay, later we will see this. It's very clear. So, so the question, okay, the question we're trying to answer this week is, okay, given a material, okay, can you predict the refraction index of it, right? And how do you understand where the refraction index comes from? Okay, and then the first question I probably we're going to fail anyway is that the classical model is not accurate at all. Okay, it kind of gives you an idea where the refraction index comes from, but it never tells you the accurate number. Okay, so here it's more about the physics picture of what refraction index comes from. Now, if we turn back, okay, to the Maxwell equation, what we see is that the refraction index, previous week, we showed that the refraction index square is the relative permittivity, right? So the whole idea, okay, the key, okay, of everything here is trying to understand where the relative permittivity comes from, and in and in a deeper way, okay, what is really the relationship between the electrical field and the electric displacement field? Okay, once we understand the microscopic picture of where relative permittivity comes from, okay, then we can kind of set up the system, set up the mathematical framework for this class. Okay, so from here, okay, you can clearly see the relative permittivity is something at first, okay, at least first observed experimentally with the Coulomb's law, right? With the Coulomb's law, you have the divergence of electricity. Well, electrical field is the total charge divided by epsilon naught. If you use electric displacement field, then the divergence would be the free charge. Okay, there's a missing factor here. Okay, so let's revisit, okay, this problem of Coulomb's law, right? Suppose you have a charge, okay, suppose you have a charge, and it's inside the medium this time, it's not in vacuum, okay, and say the medium's relative permittivity is epsilon r, right, and we call this A. And then there's electrical field, okay, going out from the charge. And the question is, suppose we want to know, our question is, what is the electrical field at a given point inside this dielectric material, okay, inside it. Outside is a different story, okay, inside it. And this actually has been observed experimentally. And then I think some of you might see it in either college physics or in an EM field. The electrical field, okay, created by charge A is 4 pi epsilon and then QA, okay, R squared ER, okay, and then 1 over epsilon R, right, 1 over epsilon R. So what it means is that the dielectric media somehow, okay, weaken your electrical field. At this point, we don't know why. Okay, this is experimental measurement. Later we'll explain, but it just makes sense, right? It's, you know, you put something in between your source and then your measurement, and then it weakens your field. Just make a lot of sense. Now, if you look at this, and then you look at your Gaussian's law, okay, Gaussian's law, let's write it down in integration form. You start to see, okay, where this epsilon r might come from. This is the differential form of Coulomb's law. The integration form is, okay, the surface integration. Let's say I select the surface inside this dielectric material. The surface integral of the electrical field goes through the surface, okay, going out, has to equal to ST equal to the total charge total charge inside this area, right? This is the integration form of the Gaussian's law. Now, if you look at this equation, then you start to see something is a little bit off, right? So if you just look at this picture, it looks like the amount of charge is the same, right? You still have rho A inside this area. So on the right-hand side, the integration is the same, On the left-hand side, somehow, your electrical field is weakened by your relative permittivity, right? So the left-hand side becomes smaller, And what does it really mean, right? Anyone knows the answer? Probably not a good idea to ask question in a small class. Yeah. So so what really happened is that the Gaussian's law is correct. This one is of course correct. Otherwise, we wouldn't put it in the Maxwell equation. And then also the this electrical field equation is also correct. It's an experimental one. So what really happened is, what really happened is actually in the media. Let's just erase this first. In the media, this charge density actually changed. This charge density actually changed. So suppose we follow this line. There's electrical field, right? And then we know that this is the part that we kind of use some knowledge from the 20th century. We know that at this part, we know that the media is composed of either molecules or atoms, right? And molecules and atoms, they have electron, which is negative charge, and then you have nuclear, that's positive charge, right? And they will actually move, mostly just the electron, but let's say they will actually move because of your electrical field, right? So the positive charge would tend to move away from this positive charge, create a positive one here, and the negative one will be attracted to your charge A, so the negative one is here. So inside each molecule or inside each atom, your electron will be pulled a little bit away from its original position, right? Away from the original position, and we call this the electric dipole. This is a dipole because one has positive, one has negative. And this happens everywhere inside your media, right? It happens here. It also happens here. Happens here. And if you see that, then very close by each other, the positive and negative actually they will cancel each other, right? They're very close to each other. So this everywhere in the middle, everything get canceled out except right at the boundary between your charge and the media. And also right at the boundary between your media and the vacuum outside. So what really happened effectively, you can think of, is that in the media, each molecule moved a little bit. The electron in each molecule is moved a little bit because of the electrical field. And then the net effect is that it looks like some positive charge is accumulated as the boundary between the media and the vacuum, and then some negative charge is accumulated between the boundary of the media and the charge. And now, if you now draw an area, you draw an area, try to do the integration form of the Gaussian's law, then then what you see is that inside, okay, what you see is that inside the charge density actually can be split up into two parts, right? One is the free charge, that's the charge A that generates the entire field, okay, free charge, charge A. And then the second part is the charge that is induced by this electrical field, okay? Let's call it bounded charge. The reason we call it bounded charge is because they are actually just polarization inside each molecule, okay? The electrons moved slightly by the external field. They can't really, this charge can't move freely, okay, inside your media, so that's why we call it bounded charge. Epsilon dV, okay? And then here we know that because there is a circle of negative charge surrounding your source charge A, so this integral actually becomes smaller than if you just have the charge A in a vacuum, right? So this is smaller than rho A, okay? So this is actually how the electrical field, the Coulomb's law of electrical field in media, in permittivity media, agrees with Gaussian's law. Okay, this is how they are keeping themselves self-consistent. Okay, and the key concept here is that you can create electrical dipoles. And if we write down the kind of the chain of reaction, is that you have electrical field, that's E, that polarize, okay, polarize a matter, which generate dipole, okay, which in effect change your electrical field afterwards, right? So this is electric field to matter back to electrical field. Okay, this is the chain of reaction. Okay, and some of you might already start to see a problem here, is that this is using the static electrical field, right? But then when we talk about light, it's actually really about oscillation field, right? Light is really oscillating very fast, and then the electrical field inside. So whether this equation, okay, whether this idea is correct or not, or whether the material can respond quickly enough to follow the change of the electrical field inside light, okay, that's actually a very interesting area to explore, especially when you go to extremely high frequencies like deep UV or X-ray. Okay. Okay. Now let's see here. Okay, the next question we'll have, okay, after understanding the way that you generate relative permittivity is because you have dipole, and then because you have all this electrical charge redistribution. Now our question is, so what is the right way to move forward? Right? What is the right way to move forward to integrate this, okay, the charge thing, really into the Maxwell equation? And we know this is the linear regime, but it actually doesn't work that well. Just look at one example here. Let's say you have charge A, and then okay, it's inside a media, epsilon 1, and then connect to another one, epsilon 2, and then they all inside another media, epsilon 3. Okay. Now I ask the question, what is the electrical field here? Right. So if the media itself is actually complicated, this idea, okay, this equation we get from the uniform media actually fall off quite quickly. Because if you want to solve this, you kind of have to know the charge distribution okay, inside this entire thing. And that's a horrible thing that you might not want to solve, right? Of course, nowadays, you can use computer, okay, to help you with that. But back in the days when all the theory is established, that's actually a very difficult charge, and then people prefer not to do it. And also today, we still prefer not to do this, even with very powerful computers. So what physicists would do, a typical thing that we do all the time, is to be lazy. Okay, is that whenever we see something that we don't want to calculate, we try to find a way to separate it or ignore it. Okay, and the way that we can do it is that if you look at it, this equation kind of already tells you the story, right? You can, well, there are two types of charge. One is a free charge that can move around by you. The other is a bounded charge that's induced by this electrical field that cannot move around freely. Okay, it's just a polarization. So of course, okay, we want to calculate the free charge because we have control of it. And we don't want to care about the bounded charge. So what we do is that we define, okay, we define the electric displacement field that has nothing to do with bounded charge. Okay, that's the first step we do. It looks like a little bit like, well, what's the point of this? A lot of things, actually, a lot of nice things happen because people are lazy. Okay, so let's just stay with this for a moment. So definition goes this way, okay, as you can see here. The Gaussian's law, okay, this is the Gaussian's law. And where rho is the total charge, okay? And just to avoid all this trouble, people define electric displacement field. It's a field that also satisfies the Gaussian law. Okay, but the charge is actually generated by the free charge. It has nothing to do with the bounded charge, the induced charge. Okay, then what you can see here is that as total charge equals to free charge plus bounded charge, then you can actually set up an equation that connects these two, right? So what you will have is that you will have, let's move it around here, it's minus, let's say. Free charge equal to total charge minus bounded charge, right? Because free plus bounded equals total rho, total charge density. What it tells you is that, okay, free charge equals to divergence of electric displacement field. Okay, total charge equals to divergence of electrical field. Okay, and then you're left with the bounded charge. Okay, you're left with the bounded charge. And you can kind of see that, okay, displacement field is the field generated by free charge. Electrical field is the field generated by all charge combined. Then bounded charge, there must be a field generated by bounded charge. Right? There must be a field generated by bounded charge. And people define this as the polarization. Okay, define this as the polarization, which you have the divergence of polarization, okay, equals to the minus of your charge density, okay, of your charge density. So let's put this definition here, D equals to and then P equals to the let's use prime, okay? Prime represent the boundary charge, okay? So this is the definition, okay? This definition kind of help you, okay, if you are in a case where you don't want to care about the boundary charge, you can just calculate the displacement field first, and then worry about the boundary charge, okay? And the second thing that's nice about this is that the second thing that's really nice about it is that the boundary charge actually summarizes the material response of your electrical field, right? If there's no boundary charge, then it's the same as in vacuum. So all the response, okay, all the interaction actually between light and matter is all summarized in this polarization field, okay? So that's why we're actually bringing out, okay, because it tells us the story between light and matter interaction, okay? And we'll actually spend a lot of time to, work on this and then see, what type of things we can generate from this one. Okay, any questions so far? Okay, so far what we do is just tell you what the material response of light came from, okay, and then how to separate them into a specific term that's called polarization. But then we actually never really go anything deeper than the original original Coulomb's law, right? Just definition. Now, what we can do here, okay, is to show you guys the missing, okay, factors here, missing factor, how can we actually connect this to the actual material, okay? The missing thing, if you turn to page 2 to your lecture note, is actually the microscopic point of view for depolarization, okay? Microscopically, how the polarization is actually generated, okay? It's generated. So if you guys look at this dipole here, okay, there's electrical field that generate a pair of dipole, okay, pair of dipole. Locally, for material, you can actually calculate this, right? For each molecule, if there's an electrical field, external electrical field, you can kind of predict, if you know not everything about this material, you can predict how much this positive charge will move to the right and how much the negative charge will move to the left, right? And suppose you know that, okay, then there's a connection. There's a connection between the there's a connection. Let's say the amount of movement of the charge to the center, okay, to the center is r. Okay, there's a distance it moves. It's r inside a molecule. So inside a molecule. Well, it's a very large molecule here. Then the polarization, okay, the same polarization defined here, equal to the density of your molecule, okay, the density of the carrier, times the charge that each molecule carry, right? At least each molecule that contribute to this polarization, right? For example, even if you have for a large number atom, right, you have a lot of electron, but only the outer shell that participate, okay, in all this electric-magnetic behavior. Then in that case, you can say the carbon has more electron than hydrogen, right? And finally, times the average, okay, average dipole displacement, right? So this average is actually important because, like, if your material, okay, somehow, usually they don't, somehow respond randomly to your electrical field, right? Then they can all cancel each other from different locations. So this kind of equation, if you look at it, it kind of makes sense, right? It tells you that if you have more dipole, okay, you have more polarization field, right? If your dipole has more charge, then you have more field. And then if you have larger dipole, right, the dipole displacement is larger, then you also have more field, okay? So this equation kind of intuitively, okay, it makes sense. And if you want to prove, okay, if you really want to prove this microscopic definition of dipole, okay, agrees with the macroscopic definition that we define from the Maxwell equation. That's a few pages of mathematical calculation, and then you can actually find it in the classical electrodynamics. I think that's the Jackson's book, the famous Jackson. Classical electrodynamics book by Jackson, chapter 4, okay. There's about a few pages that kind of convince you, okay, this equation is correct. Then, here, okay, I just ask you to believe me, okay. And from here, okay, with this connection, what you will see is now you can finally establish a connection between your knowledge of the material and actually the microscopic knowledge of the material and macroscopically how it responds to the light, right? If you know each molecule, how would they behave in terms of the with the external electrical field applied, right? How many of them, how much charge it has, how much displacement you will have, then you can know, okay, the polarization. And once you know the polarization, you can actually directly bypass this, right? You can skip this step, right? Directly come from here to here, right, back to the D, and then get your electrical field. So this way you don't have to calculate the charge distribution anymore, okay? You don't have to calculate that anymore. Okay. Now let's do something very simple. Whenever we have a new equation, okay, and then someone asks you to believe them, you kind of have to check something by yourself first, right? First is that the dimension, right, or the unit of the left-hand side and the right-hand side, right? And here, the left-hand side is the polarization, and the polarization, of course, have the same unit as epsilon E, right? Because they two add together give you the displacement field. So what we can do here is polarization has the same dimension, okay, as epsilon E, and then we know E, right? E can come from the Coulomb's law. So it's a charge, Q, okay, and then 4 pi epsilon, and then, okay, this is the 1 over distance, right? So you cancel the epsilon, 4 pi is just a number, so this gives you charge over length square, right? This is the dimension of displacement field. Right? If you look at the right-hand side, N is the number of density, right? How many molecules you have in a certain volume, right? So the dimension here for the N, right-hand side, N is actually 1 over L to the third, right? So it's like number versus volume, okay, number versus volume. And this one is just Q. Q is charge. And then the third one is the distance, right? How much your dipole move, well, how much your electron move. And that's also a dimension of L, right? So if you combine these two, then it's Q L squared, right? So it's actually the same dimension. So this is the first check, okay? The second check, of course, you want to make is that this is a field, okay, a field generated by. This is a field generated by your dipole, right? And then if you look at it, the field actually has similar form. Okay, it's in the same equation. Should have similar form as the electrical field. Right? So the question you have, of course, is that, okay, for this dipole, a pair of dipole, is it really true that when their distance between the two dipoles is larger, is it really true that it's generating more electrical field externally? Okay, the field it generates, is it really linear with the distance, okay, between two charges? Okay, and then the other two are kind of straightforward, right? The more you have, the higher the electrical field. The Q, okay, the more charge you have, the larger the field, right? So the key is really, does it make sense for a field generated by dipole, okay, to be linearly related to the distance of two charges inside a dipole? Okay, so for this we can make a very simple calculation, and then kind of just to convince you guys this is the case, and you can really believe in this linear relationship. The situation that we can calculate is that suppose, okay, there's a dipole, and the charge, of course, is the same. It's plus Q minus Q, right? Because the molecule itself is neutral. And then the distance between the middle point to the charge is r, okay? And then let's say far away from this dipole, we ask the question, what is the electrical field? Right? What is the electrical field far away from the dipole? And of course, this is a three-dimensional question, okay? And just for simplicity, we only calculate one-dimensional. Okay, the one that the electrical field along the direction of the dipole, right? And if you want to know, okay, how this how the electrical field distribution of the three-dimensional, then you can actually check the Jackson's book again, okay? And then again, it's a few pages of calculation, but you can kind of guess it's a balloon shape, double balloon shape. Okay. So let's do this calculation. It's fairly straightforward. Let's say the distance between the electrical field position and then the center of the dipole is d. And then you can write down the electrical field here because it's all along this direction, so we can drop the vector sign here. And what we will get is Q 4 pi epsilon. Okay. And then the positive charge, its distance between the positive charge and the the place where you want to look at the electrical field, it's d minus r, right? This is the distance, okay? And the distance between the this position and the negative charge is d plus r, okay? D plus r. And then, of course, there's a minus sign here because this is a negative charge and this is positive sign, so it's positive charge. And now we're going to use approximation that you have probably already used many times, or you're going to use many times in this class, and hopefully in your future career, is this very simple approximation that the polynomial, okay, 1 plus x to the y power, and this one would approximate to 1 plus x times y when if x, the absolute value of x is much, much smaller than 1. Okay? You can prove this by doing a Taylor expansion of this polynomial. Okay? And then you will see that there's higher power term x squared, x to the third, x to the fourth. And that's why, okay, when your x is small, you can drop all these terms and then only keep the first two leading terms here. If you use this approximation, then back in here, then what you can do is that, let's use the first term. Well, let's just write it down here. Okay, let's look at the first term. So the first term is d minus r, okay, to the power of minus 2, right? That's the 1 over something square. But the form here you see is 1 plus x, right? So, and x is very small. So is there a value that's very small here? Apparently r is very small, right? R is much smaller than the size of a molecule or atom, right? It's much smaller than the distance that you will be interested to, okay? So r is much, much smaller than d, which means, okay, if you divide that d on both sides, r divided by d is much, much smaller than 1, okay? So what you can do here, is that you put the d out, okay? So d minus 2. And then become 1 minus r divided by d. Okay, 1 minus r divided by d. The other way you can think of it is that, okay, you can divide d squared, okay, both up and down, and this way you can get this d to 1. Okay, and then you can do the same thing to the right-hand side, d minus 2, 1 plus r over d. Oh, by the way, I forgot to mention that we need to end this class at 12. I have another meeting I need to attend to discuss about what I need to teach next semester. Okay, it's kind of funny. Anyway, okay, then let's apply this approximation. So q 4 pi epsilon d squared, okay, d squared, and then 1 plus, okay, 2r divided by d, right? This is using our approximation here, minus, again, 1 minus r divided by d2, right? Okay, using exactly the same approximation. And then you can see that this 1 will cancel each other. 2r divided by 2, these two terms, okay, they are the same, so they stay. And then you, okay, 2 plus 2 is 4, cancel out the front term, okay, so it's q, and then pi epsilon d to the third times r, okay, times r. So see that this is the electrical field. So you see that the electrical field actually goes, proportional to the distance between your dipole. Okay, and this is exactly what we, expect from this expression of polarization and the dipole. Okay, the second thing that you guys probably notice that is d to the third in terms of the distance between the dipole and the charge. Between the dipole and a far distance, right? So it's not the 1 over r squared law anymore. So this is actually why, okay, in chemistry, you will learn that there are many types of interaction, like van der Waals, that they doesn't follow 1 over r squared. Okay, it doesn't mean that there's a new type of interaction. It doesn't mean that. What it simply means is that the charge is collectively distributed in a way that when you look at it from a far distance, okay, the charge inside a molecule and the charge inside a material, they look like they can produce an electrical field that doesn't have 1 over r squared. Okay, it can have other laws. And most of these interaction, if it's 1 over d to the third, you can tell it's actually, it dies off much quicker than over r squared. Okay, so it's actually a short-range interaction. Okay. And you can actually kind of do the same thing for the nuclear physics. Okay, it's the same thing that there are quarks. Okay, and of course it's not as simple as this, but then you can kind of think, okay, when they combine together, okay, they will actually have a different type of interaction range, and then some of the force fall out quicker, some of the force fall out slower. Okay. Any questions here? Okay. So far, the most critical things we learned in this class, okay, in addition to EM field, which you guys are familiar with, is that there's a connection, okay, between microscopic polarization, how each molecule responds, to the macroscopic polarization that can help you to solve electrical field. Okay, and you can kind of imagine now what we are going to do in this class is that if each molecule responds differently, okay, to the electrical field, then we will generate very different phenomena. Okay, and the very first thing you probably have already imagined in your head is that does the electron really has to follow linearly with their electrical field? Right? Does it really have to move linearly? Right? If you look at the molecule, right? Well, let's say atom. It's a miracle that it changed linearly, right? Because this is especially when you do quantum mechanical calculation. Let's say you have 1 over r squared. This is your electrical field. This is the electrical field between the nuclear and the electron. And then now you add electrical field, right? And what will really happen is that the orbits or the cloud, okay, kind of shift towards that way, okay? And then it's only linear when this change is very small. It's kind of the same idea as what you do with the Taylor expansion, is that when something is small, then you can neglect all those nonlinear terms, okay? But if something is large, if there's a strong field, then your molecule will be destroyed a lot, and then you can't expect it to respond linearly to you. Okay? Now we'll talk about this in detail later. Okay, later today and also on Wednesday. Now we'll spend 10 minutes to introduce a very simple model that later will help us to understand. Okay, to just understand what's going on inside a molecule. Right. The simplest model, okay, the classical model, which might be too simple to be true, and then of course it's actually not true, is called a harmonic oscillator model. Okay, so the idea is that it actually makes a lot of sense intuitively, but of course because it's not quantized, it's not, it doesn't agree. Well, it's not. It's a classical model, so of course it's the number it predicts is wrong. But it tells you all the phenomena you might get. So suppose there's no external field, okay, just a charge sitting inside a material, right? Sitting inside a material. It can be a molecule, it can be a semiconductor, right? It can be metal, right? The charge doesn't really sit in one of the spot. But when there's no external field, what you can expect is that those charge will tend to move to the place where where it has the minimum potential energy, right? It's like if you have, let's say this is the potential energy Vx, and let's simplify to one-dimensional, okay, x, right? Let's simplify to one-dimensional. X is a position where your electron is, let's say x, and okay, and there's an effective potential, well, Okay, effective potential, well, for example, in the molecule in the atom, right? The ground state of a charge is a certain distance away from your nucleus, right? So that's your minimum potential energy position, and your charge, okay, your charge or your electron in this case would tend to stay here, right? Would tend to stay here. It's as simple as you throw a basketball or throw a baseball, down, and then it will fall to the lowest point, right, nearby, and that's the gravity, right? So this is the same thing. It's a field, or it's a potential field that created by inside your material, okay? And for most of the materials, we can actually know what the potential field looks like. Okay, you can actually write down equation, example Vx. Okay, the reason that we can draw it out. Okay, Vx. Okay, and because we already know that the charge, okay, would tend to stay at the lowest point of this potential well, then what we can do at potential well, and also we know that the charge will move very, very slightly, right? Very, very slightly when there's external field applied to it. Let me try to give an example here, right? So if the charge really move far away, okay, kind of become free, right? Think about it. What are the chances when you shine a laser, or when you put a piece of glass under the sun and then somehow you generate free charge, right? If that's simple, then you have a very cheap generator, right? Electric power generator. That don't happen, okay? And you can further argue, okay, if that's the case, then there should be no human being. It's because our molecules are so unstable under the under the daily sunlight activity, and then probably no life will be created in that sense. Okay. Then if we assume, okay, if we agree that the charge, okay, will move very slightly at the presence of external field, then what you can do here is you can do a Taylor expansion, right? You can do a Taylor expansion near the minimum potential well position, and okay, and then the first order is the absolute potential energy. That really doesn't matter, right? You can kind of raise and lower the potential energy by a numerical number. That doesn't matter. You can always define this to be 0. Okay, but of course, when you bring two molecules together, and then you try to compare the relative potential, you cannot assume both of them to be 0. You have to compare the relative difference. And then the first term, okay, you would think is a linear term, right? But that linear term, vanish is because you're at the minimum point, right? The minimum point, the slope at the minimum point is always horizontal. Okay, it's always 0. Okay, otherwise it will keep falling, right? So here, actually the first term is a square term, okay, and then you have a third term. And keep going. Okay, it's just a very simple definition of the Taylor expansion. And the reason we write it down as 1/2 kx squared is to draw the similarity, okay, between this and the harmonic oscillator, right? Because we know that the force generated from a potential well is the derivative of the potential energy, okay, and minus sign here, right? So if you take a look here, then what you will get is minus kx, okay, minus alpha kx squared, and keep going, right? So the leading term here is actually like a harmonic oscillator, okay? There's a restoring force whenever your electrical field tries to pull it away from its a most comfortable position, then the there's a restoring force to pull it back, okay, and then it's like a harmonic oscillator. So that's why actually harmonic oscillator is very important in in a lot of physics subjects, and then for example quantization of light, and a lot of these are based on harmonic oscillators. Okay. Let's see whether I should introduce it here or leave it to next class. Okay, I can quickly say it here. Okay, so one thing you can do, here is that now it's a charge of Q, and then it's actually electron trapped inside a potential well, right? So what you can write down is that it's actually very simple. F equal ma. Right, it's as simple as this. F equal ma. Okay, to predict its motion, right? Ma is very simple. You can write down m x double dot. Double dot means twice derivative, time derivative. Okay, equals to the force, and then the force. Well, there's a force, of course, is the Q E. Right? This is a force that your electrical field, external electric field, apply to your charge. And then there's a restoring force. Okay, a restoring force that's minus kx minus alpha kx squared. Okay, keep going. And then there's another force that we kind of want to introduce here, and then I kind of wish that you guys can understand this as intuitively, is that if you ever move, right, if you ever actually build a harmonic oscillator and let it move around, what really happens is that it doesn't move indefinitely, right? At some point it will slow down and stop. And what really happens is that there's a friction, okay, between your harmonic oscillator and whatever supporting it, right? And this friction, okay, can be kind of understood as a dissipative channel, right? It kind of dissipates the energy from your system harmonic oscillator to the surrounding environment. Okay, so it's the same idea here, because the electron is kind of surrounded by all the materials, right? All other electrons and atoms. When it starts to move, it doesn't necessarily conserve all the energy within this electron, right? So there's a chance that the energy can be dissipated to other places. Right, so you can kind of use the same idea as, okay, there's a friction force here, and this friction force usually is proportional to the velocity, okay, the velocity of how it moves, okay. So so because of that, there will be a force introduced here. Okay, that's minus gamma x dot. Okay, this is like the velocity. Okay, it's a minus sign because they also try to slow down. Okay, try to slow down the motion of the charge. Okay, and then we will stop here, and then next class we will kind of solve this for you guys, and then see what the solution can predict in terms of refraction index, and then kind of answer a lot of questions from here. Okay, thank you guys. Any questions?